Hi, everyone. Am I speaking close enough? Yeah, seems so. So, hi. My name is Julien Loudet, as mentioned, and today I want to present Eclipse Zenoh, what we believe is a communication backbone for ubiquitous and heterogeneous AI use cases. So, it's Gary already mentioned in his presentation Zenoh and OpenCV, so I want to tag along and say that we're already doing some demonstration using OpenCV and Zenoh. So I have another talk tomorrow where I will have a video of this if you want to follow along. So what do we mean by ubiquitous and heterogeneous? What our current understanding of how AI is done right now is we have everything going to the cloud. And so in an increasing number of cases, what we want is, because we have more and more computing power in our devices, and maybe for reasons, proprietary reasons, you have information in your house that you don't want to send somewhere else. What you want to do is be able to use all that infrastructure, all these different devices, and have them communicate. So eventually you end up in a system with lots of devices, and if you keep using today's technology, it's not meant to. So eventually, if you want to have something that spans on all these different devices, mixing everything, you end up with what we call a digital Frankenstein. To be correct, the digital monster of Frankenstein. So the idea is you will have to patch technologies together in order to have data flow from, for instance, your smartphone to then your edge technology, and then you need again to patch from that to the cloud. And if you want to have something where data flows end to end, eventually you will need to do a lot of stitching. And this is not a problem that we have only in AI. This is something that you would find in other industries, for instance, in robotics, in automotive, IoT. And what we believe a solution is, and so this is the first and main important part of my talk, is to tell you that if at some point you will need and you will have these problems where you have multiple devices connected, and you will need a technology that allows you to address each of them, that is powerful enough to address all of them and flexible enough to adapt to dynamic changes. And so we believe the solution is Zenoh. So as you can see, the black dragon is our logo. We have a few comics if you follow us. And so what is Zenoh? And that's going to be the second part of my talk. So I'm going to explain how Zenoh fits. So Zenoh is a publish, subscribe, and query protocol where we unify data in motion and data at rest, as well as distributed computations. We want to target everything down from the microcontrollers and up to the data center. And for that, we're providing location transparent abstractions, as well as great performance. So as I already mentioned in the slide, we want performance, so we already have support for zero copy and shared memory. Okay, so this is Zenoh. So how does it fit the bill? How does it go everywhere? So we have first multiple programming APIs and multiple programming languages, even though the core is written in Rust. But we also, when we say we want to go everywhere, we mean that we don't necessarily require a TCP IP. So in Zenoh, you can implement your own transport, and if you want to implement your own transport, what we require is only a data link. That means that if you want to connect your devices, you can, for instance, use Bluetooth. You can use serial, you can use Unix sockets. So really, Zenoh is aiming to be a protocol that allows you to connect everything seamlessly and easily. Speaking of still of running everywhere, we have support for major operating systems. For those that are interested in safety critical application, we have also QNX integration ongoing, embedded targets, AutoSAR. So I mentioned, so we have more and more devices. AI is going to leverage all those devices. You have small sensors in your factory. You want to do some part of the computation at the edge for many different reasons, and then maybe offload the average to the cloud. So what topologies do we support? So looked better on my laptop. We have peer-to-peer, so if you want to connect them in a click or in a mesh, Zenoh supports it. Now, if you have devices that are quite constrained, don't want to send too much information, because most of the computing power will be used by AI, then we support the brokered communication with routers, and then if you want to structure a bit more your infrastructure, we can use also the routed topology. So, and if still you need to integrate more technologies, Zenoh is easily extendable. We already have plugins. So for instance, we have plugins for different storage backends, namely InfluxDB. So if you want to do time series and you want to analyze, let's say, pollution somewhere, you can use that. This is all and great, but for now, this is just me saying that this is good. So what are people saying about Zenoh, about adoption? So here we can see, and I will come back on this tomorrow, Zenoh has been selected as the ROS middleware, but we have different milestones of successes. So not to go through that slide, everything, is to say that we have been recognized as innovative startups. We have been integrating in U protocol, which is for software-defined vehicle. We've been selected as the best protocol for robotics and even recommended by ITU. We, as I mentioned, are the new robotic middleware for ROS. So starting in the next release, which I think is going to be later this year or in 2025, by default, if you're using ROS2, the middleware you're going to use for it to communicate is going to be Zenoh. Amazon also said some nice things about us. So to quote them, we're the most viable protocol that will help them mature their model, Eclipse Zenoh. Where we've been compared to other middlewares such as MQTT, DDS. And so, but this is not the only thing that's running on Zenoh. We already have internet scale analytics platforms. We have some blockchain, starting blockchain project that we're using Zenoh, also automation platforms. And I didn't put a slide on it, but we also had one small AI company that was using Zenoh in order to distribute the computing load across different nodes. So, okay, so with this, I hope I've shown you that, okay, if you're in a setting where you have lots of devices and you need to connect them, and if you want to do some AI computation, for instance, at the edge to save some bandwidth, be more ecological for sensitive information, then Zenoh is one of the protocols you should consider. So now the second part of my presentation is going to be, okay, what are the main concepts? How do you use Zenoh? So first thing that I need to talk is about the abstractions we're using. So we're in Zenoh, we are publish subscribe, and so what we use are resources. We have composed of a key and a value. So you can see, I don't know if I have a pointer. Yeah, I do. So key and a value. So this would be your key, which is a key expression, and with the value, which is any payload. So what's a key expression? So it identifies a set of keys. So here we have special characters, the star and the double star, which we call wildcards. They allow you to target a set within your network. So if we're thinking about devices and you're thinking about what you want to do with AI, if at some point you want to get all the temperature from your sensors in order to obtain a trend, then you could use these star in order to target all your devices. And this is purely dynamic. You don't need to know ahead of time how many devices you have. Then we have, if you want to have a bit more power querying your device, then you can add selectors. So these are the main abstractions. So resource, we're using in Zenoh. So PubSub, as I mentioned just earlier, what is it used for? So the idea with PubSub is if you have several units that are interesting in the data produced by a sensor, then you could subscribe, and then only the subscribers that are matching the key expressions here will receive your data. query reply. So we said that we do pub/sub, but we also do queries. So a query is basically an on-demand request to a matching key expression. So for instance, and this is where the data in motion and data at rest as well enters. So for instance, if you are joining the room later on and you want to do some recover some data, then the query reply combined with the storage will allow you to get the previous values. So it means that if you want to retrieve what was published before, you could use a query for that. The same idea applies, only the queryables, so a queryable is declared on a key expression, only those that match will actually send the data. Distributed storage. It's, the idea is, what I also expressed with the query before, is to retrieve data on demand. So basically, not basically, a storage in Zenoh is the mix of a storage, a subscriber, and a queryable. So the subscriber will actually obtain all the data that is being published, and then the queryable will allow you, whenever you want to retrieve what was published, to access previous publications. Okay, now with hopefully an animation. So the idea here is we have a set of publishers. So we have two publishers here. We have different storages here and there, and we have subscribers. So if the animation works, we're supposed to, yeah. So the idea here is we have that car publisher that is publishing its data. And so we see that Zenoh is routing the data that is being published to all the storage that are declared on fleet 1, because that car is fleet 1, and here we have the wildcard. Similar here, we can assume that this is some kind of live display that you want to do of your infrastructure, of your car fleet, and then you would have a subscriber that is here is subscribed to fleet star, so that match either fleet 1 or here fleet 2, and then for all the cars you want their position. Next, the idea here is to show that even though these storages, so they're all connected, and even only the subscriber that match here will receive the publication. So in here, fleet 1 went to the subscriber, similar here, fleet 2 went to this, but it didn't go there because the key expression doesn't match. So now we want to do a distributed query, so we want to retrieve something from all the cars of fleet 1, and so what we're doing is that we can see here we have access to, we are targeting the storage here and there. But we also have a storage here that would match that query, and this is one of the properties of Zenoh, is that depending, okay, need to let the animation go. Depending on where you do your query, Zenoh will be able to detect where is the storage that is closest to the data you want to retrieve, and then only target that storage. So in here, we are making exactly the same query, but we targeted different storage. So these properties are configurable, but makes one of the powers of Zenoh. So I mentioned in my previous slide that all the nodes are connected, and I didn't say how they're connected. So to do that in Zenoh, we have two aspects, scouting and discovery. So scouting is not part per se of the protocol. It relies on UDP multicast to work. So that means that if you have a Zenoh node on your LAN, and then you connect other Zenoh nodes, they will automatically discover each other. And this, you don't need to configure anything. Now, if you don't have that and you need to connect, for instance, nodes that are on different local area networks, we give you the possibility to connect the routers that are on different LANs, and then rely on these routers to do the scouting and to discover other peers on the network. And so the other part is, if these two routers are connected and they have discovered in their local area networks the nodes, then how do they know of the others? And so this is the second aspect, which is discovery. So Zenoh uses GOSIM in order for routers to exchange information about the routing information. Okay, so a little bit of programming API, just to show you one key element is that with Zenoh, we're trying to focus on simplicity. I hope I've showed you earlier that everything you need to do, like Zenoh will try to do the maximum for you to discover nodes. And so now we want to show you the same for APIs. So Zenoh, because we want to target from microcontrollers up to the data center, we have different implementation. We have the core that is in Rust, but we also have Zenoh Pico that is targeting microcontrollers, which allows us to really diminish the amount of memory consumed, both by the binary, but also during the exchanges. We have bindings in C++, Python, if you want. This is what was used for our AI demos. And so how do you open a session? So a session is what allows you to communicate. It's a one-liner. You need a default configuration. So this is in Rust for those not comfortable with the language. How do you publish? Well, we have, you just simply declare a publisher. So this allows us to do some network optimization. So if you want to reduce the amount of bandwidth that is being consumed, just need to declare your publisher. And roughly summarized, we are going to translate these to integers in order to diminish the amount of bandwidth used. But also for simplicity, if this is a one-time publication you want to do, and this is again one of our goals with Zenoh, is to be as simple as possible. We can do this on a one-liner. Sorry. Similarly, publisher, how do you declare a subscriber? It's the same. So just, I went quickly. So the Z here corresponds to the Zenoh session we opened. So we have one line to open the session, and then another one just to declare a subscriber. Then you can add a callback, or just wait, use streams, etc. So I mentioned payload, and in the previous slide, you could see that I did not do any specific transformation in order to send the data across the network. That's because for these simple examples, we provide with Zenoh a default serializer and deserializer, but that is for convenience, because ultimately Zenoh transports bytes. So as such, any serialization framework will work. If you want to use protocol buffers, if you want to use Apache Arrow, or if you want to use flat buffers, then they will all work with Zenoh. If you look at our documentation, we even have examples for protobuf. Now, I don't have the time to go through absolutely all the features we have, but to give you a rough summary, so additionally we provide reliability. So the idea here is, because we're a communication middleware, you need maybe at some point to have some guarantees on your communication. This allows us, depending on the available transport, to choose the one that is most suited. So if you want something reliable, maybe use TCP. Congestion control, this dictates how in Zenoh, if you have the queues filled up, how to drop messages, and if to drop messages. Priorities, if you have more sensitive, for instance, control traffic, you might want to give a higher priority to this compared to data. You can use that with priority configuration. We have consolidation. So consolidation has to do with distributed queries. So as I mentioned earlier in the animation, you can make a query that could target several storages. And so the idea of consolidation is to give you the tools to tell Zenoh how to consolidate that data. Maybe you want to keep only the latest value. Maybe you want to keep all the replies. Maybe you want to do some other operation. This would be controlled with consolidation. Additional feature, liveliness. So this is kind of the concept of group management. You want to have several nodes that you want them to make them belong in a group for different use cases. Maybe that would be a fleet of cars. You want to know how many are there. So liveliness would be a way to do that. Attachment, not similar. It's again for the get. Maybe you want to send more information to change the behavior of the computation, and so attachment will allow you to do that. Matching listeners, so this is to detect if you have a publisher. So this actually allows me to give another nice property of Zenoh, is that it will only send data to the network if and only if there is a subscriber. So for instance, if you have a publisher and no one is interested in that publication, so no one is subscribing to it, then Zenoh will not send data. Publication locality controls, well, if you have a publisher and a subscriber on the same key expression on the same Zenoh node, maybe you don't want that to listen to you don't want to listen to your own publication. So locality controls this. Okay, so I've mentioned at the very beginning that our aim is to be performant, and so how performant are we? So yes, this is big enough. So we've run, so this is a benchmark realized by a university, and they basically try to measure the performance between Zenoh, MQTT, Kafka, and DDS. So basically the three lines here, so which are the lines, basically it's easy. The lines at the top are Zenoh. So the different version of Zenoh has to do with how we compiled Zenoh. Did we use the Rust core, or did we use the C or C++ core? And the rest, so in blue is DDS, our own implementation of DDS, Kafka in orange, and MQTT. So what we can see here, this is the number of messages per second that Zenoh can send, depending here on the size of the payload. So we can see that some protocols are not able to send more than a specific payload size, whereas Zenoh goes from 5 million messages to, well, if you need to send 500 megabytes, then we can send that 12 times per second. On the bottom, what you can see is the throughput. So how much gigabytes Zenoh is able to send, depending on the size payload. And we can see that we very quickly, so here with 256 bytes, we're able to already saturate a 10 gigabyte network connection. I think this summarizes well. So, and I'm reaching the end of my presentation. So I have presented Zenoh. So our purpose here is to facilitate distributed systems. So we believe that the new systems you're going to have are going to be comprised of many different devices with various computing powers. And so you might have your sensors that will only process a bit of data and then send that to edge infrastructure. And that edge infrastructure will do some, for instance, some inference, any machine learning algorithm. And so we believe that in order to do that, and especially that setting where you would have a dynamic environment, you need a communication middleware that is both powerful and dynamic enough to easily allow you to target all of this. So location transparent abstraction provided by Zenoh. And that's it. Thank you.